All right, so let's now wrap up this first calculation, scaling calculation, where we use dimensional analysis to figure out what the diffusion time was in terms of the two key parameters that govern that diffusion time, one of which is the distance over which we're interested in diffusion taking place, and the second of which is the diffusion coefficient itself. We came up with this very interesting and nice relationship, which is T is L squared over D, where this is the diffusion time. This is the distance over which diffusion is taking place. And D is the diffusion coefficient, which I remind you has units of length squared over time. Those are the units of that thing. Okay, so all I really wanted to do to close this out, first of all, I remind you that I posed two challenges. One of them was how long does diffusion take across the synaptic cleft, or this gap between two neurons? And then I also posed the challenge of trying to ascertain whether 16 days to diffuse a distance of 30 millimeters is long or short. Okay, so those are the two questions that we posed. And what we're going to do is first we're going to think about the sprinter, and we want to compare two times. We want to compare the time for the action potential, which is traveling ballistically, and that has a travel time, sorry, a time that's given by the distance traveled divided by the velocity. For my case of interest here, this is going to be something like a meter, which is the length of the distance between the brain and your waist, or something like that. And the velocity I'm going to take as 30 meters per second, something like that, or maybe I should say 10 meters per second. So how do I arrive at that? I know that V low, my low guess would be about a meter per second, and my high guess would be on the order of 100 meters per second, and that implies by my square root rule, I should say Sanjoy's square root rule, V low times V high square rooted, which gives me the 10 meters per second. All right, so that tells me something like 1/10 of a second in order for the action potential to travel. Now, the time for diffusion over that same distance, sorry, not over that same distance, over the synaptic cleft is L squared over D, and there the distance is 30 nanometers, so 30 over 1,000, this is in microns, and that gets squared, and then divided by, let's say, something like 100 microns per second for the neurotransmitter. So this gives me, if I work this out, 30 squared is 3 times 3, which is 10, and then, so it gives me about 1,000 divided by 1,000 squared, and 1 over 100, and this is in units of seconds. And so what I find is something like 1 over 10 to the 5th seconds. So 10 microseconds. Cool. So what we see is that the diffusion time across the gap between the two neurons is way faster than the time of the action potential. If we had been in the classroom, I would have posed this challenge ahead of time. We all would have taken a vote. And I will tell you based on experience that most people would have expected that the action potential would have traveled faster than the diffusion over that small gap. So the next thing we want to find out is something about the 30 millimeter time. So let's now figure out how long it takes to diffuse over, let's say, a distance of 1/10 of a meter. Okay? So in this case, I have 1/10 of, how do I want to think of that? 1/10 of a meter is, well, okay, let me write this out and then I'll get the right units. So this is 1/10 of a meter squared divided by 100 microns squared per second. But I need to use consistent units, so this is going to be 1/10 of a meter is 10 to the fifth, so 10 to the fifth microns squared divided by 100 microns squared per second, and that gives us 10 to the eighth seconds. And I just remind you that t of 1 year is around pi times 10 to the 7th seconds. So in other words, a year is something like 3 times 10 to the 7th seconds. So this tells me that in order to diffuse 1/10 of a meter is going to take on the order of 3 years. So this is about 3 years. So over long distances, diffusion is really highly ineffective. It's quite slow. And later we will have an opportunity to compare these two numbers. So we've worked out a ballistic time, and we've worked out a diffusion time, and we can compare those. So this one was L over V, and this other one is L squared over D, and together those give rise to a quantity which is of the form D over LV. Okay, so this 1 over this is known as the Peclet number. My main point is that a number like this, which is dimensionless, so this is a dimensionless comparison of what I might call deterministic transport and diffusive transport. And this is going to be a paradigm that we're going to come back to again and again, which is this idea of using dimensionless numbers as a way to make comparisons so that we can figure out what the dominant effect is in a given problem. So when we think of, just to give you an example, when we think about flows on the interior of an embryo, well, a molecular motor or a molecule can be entrained by the flow. That would be advective or the ballistic thing. But also they're hopping around, they're doing diffusion. And so we could ask the question, what's the relative importance of diffusion and ballistic transport? And on the basis of that comparison, we can decide, in a certain sense, how to think about the physics of a given problem. So with that, we've finished our first assessment of one of these scaling estimates using dimensional analysis. We followed the edict of Bob Austin from Princeton, who sort of tongue-in-cheek said physics isn't worth a damn unless you put in some numbers. And I think it is very important for us to put in some numbers. We've evaluated the dimensions of the diffusion coefficient. There's a lot of meat in this 20 minutes of this particular set of vignettes. With that, thanks for your attention, and we stop there.